Welcome back to another video. In this video, we're going to be taking a look at a question from the IB Chemistry paper 2HR from November 2016. Now, this question is all to do with Maxwell-Boltzmann energy distribution curves, and this is from topic 6, basically, topic 616. I'm not sure if this is from the HL portion or not, but please check that out. If it's not from the HL portion, then well, obviously SL students don't need to know about this. But anyways, let's get on with it. So the question asks, an additional experiment was carried out at a higher temperature. So this is a part of another question. The information prior to this is irrelevant for this. You don't need to have that. That's why I've just taken a snippet of this part. So there is an experiment and it was carried out at a higher temperature than the original experiment. And on the same axis, sketch the Maxwell-Boltzmann energy distribution curve at the two temperatures, T1 and T2. So T1 is the original temperature and T2 is a temperature that was carried out later. And here we are told that T2 is a higher temperature than T1. And they're asking us to sketch a Maxwell-Boltzmann energy distribution curve. Now, really what they're looking at over here from students is they want to see how you interpret this knowledge that they have given you where temperature 2 is higher than temperature 1, and how accordingly do you adjust your Maxwell-Boltzmann energy distribution curve. And I'm going to show you how to do that today. But before we get into it, what exactly does a Maxwell-Boltzmann energy distribution curve tell us? I'm sorry, I'm having some trouble pronouncing this today. So what exactly does it tell us? It basically tells us the fraction of particles which have a particular kinetic energy. That's literally what it tells us. And we can use this curve to also determine how many or the fraction of particles in a reaction which exceed the required energy for a successful collision to take place. In other words, those particles, how many particles are there in a reaction which meet or exceed the amount of energy required to take for a successful reaction to happen, which we would call the activation energy of a reaction. So let me show you what a normal Maxwell-Boltzmann curve would look like. So it would look something like this. And before I move on, the first thing we should not forget to do is we have to put the axis, the labels on the axes. I know many students forget this. I forgot about this one. And oh God, when I got my paper back, I was so frustrated. It's frustrating because you lose out a couple marks because of such silly mistakes. So don't do that. You have to label the axis first. So this is the x-axis, this is the y-axis. On the x-axis, we have the kinetic energy. I know it's a bit untidy, the way I'm writing it over here, but please make sure how when you write it in the exam, it is neat. So this is kinetic energy, and this is, oh, sorry, it's going to be hard to write. And this is going to be fraction I'm so sorry, it's so untidy. If you do not understand what I have written over here, I'm just going to write it down again. I've basically written fraction of particles. If you did not understand my weird spidery handwriting over here. So that's basically what I've written. So if you want to suppose use this graph and you want to see, okay, how many particles in a particular reaction meet the required activation energy. And if suppose the activation energy is 10, so we can go over here and we can see, okay, these many particles meet the activation energy required to conduct a successful collision or a reaction, and then all the others over here don't meet it. So that's one way that you can use this graph. And I'm just going to assume that this is at T1. So this graph is at temperature 1. Okay, I'm just going to assign it as temperature 1. Now, they've told us that in the second reaction, which is T2, they have increased the temperature, right? They have made it higher. And we all know that when you increase the temperature of a particular reaction, the particles in that reaction automatically get more kinetic energy, right? We've learned that since 6th, 7th grade. So now in T1, we know, for example, if we're looking at this is the activation energy of a reaction. And if these many particles have met or exceeded their activation energy at T1, at T2, naturally, we're going to have more particles exceeding the activation energy, right? So it's going to look something like this. Oops, sorry, that is very bad. I'm very bad at drawing, but the general thing that I'm getting at over here is that this peak, the peak of T2, is going to be shorter than the peak of T1, because when we increase the temperature, we are now adding energy to that particular reaction. And that means that more particles now actually have the kinetic energy, meet or exceed the kinetic energy required for a successful collision or reaction to take place. So as you can see, the peak, this is the peak of the graph, the peak of T2 has shrunk, it has reduced from the peak of T1. And that is because we are seeing that more particles have a higher kinetic energy. So the graph it's accommodating that, right? Before, only these many particles, in T1, only these many particles had that much kinetic energy. But now when we increase the temperature, these many particles have the kinetic energy. So hopefully that makes sense. Hopefully you can visualize what I'm trying to say. And that's one main thing that you have to remember when you draw this graph. If you come across such a question and they're telling you to draw the graph of two different reactions at two different temperatures, then remember that the higher temperature will have a lower peak and it will be more spread out. You can think of it as more spread out. Like T1, it's more concentrated towards this side, right? There's a higher peak over here. That means majority of the particles are in this low kinetic area, kinetic energy zone. However, in T2, the temperatures increases. So now we are spreading the graph across, and most of the particles have this much energy, kinetic energy. They're more, the average kinetic energy has increased. If supposing you could consider this as the average kinetic energy, now the average kinetic energy is this. And consequently, there are more particles which also meet and exceed the activation energy, which in this case, I have just given you a random example of 10. Don't draw all of this in the paper. This I've just given you an example to make you understand what I'm trying to say. Oops, okay, that's not good. Let me just go back. Okay. Yeah, so don't make that mistake. Don't draw any numbers or anything of that sort. Label the axes, draw the label T1, T2 so that the examiner knows what you're talking about. Of course, make it a bit neater than I have. It's a bit difficult for me to make it neat because I'm drawing this on a laptop, but hopefully you get the idea of what I'm talking about. Don't forget to label the axes either. That's it for this video. This is it. If you do this, you will get the 2 marks that this question carries, which is quite a bit, and it's very easy. Hope you understand. Thank you so much for watching. If you have any other questions regarding this concept or any other concept, feel free to message me. I'm always available to reply to your questions. And that's it. Take care of yourselves. Goodbye. I'll see you in another video with another question.